Okay, let's do some RL parallel circuits, and these are pretty easy, and we just have to learn those formulas just as we do. We have to write them down, we have to apply them. So nothing new here, just a little different take. Now, inductors and resistors have certain, in parallel, in series have certain characteristics, and they do in parallel as well. So in series, we know that IT was equal to IR, which was equal to IL, and in order to get overall voltage, we had to apply that formula we see there, EA equals square root of ER squared plus EL squared. So it's going to change a little bit now, and this kind of draws back to some of our Ohm's law stuff. We got some differences in parallel, and that's the voltages are the same when there's a resistor and a coil in parallel, but current is going to differ a little bit, or actually a lot. So we're going to see that as we go through, and you need to go ahead and write that formula down now because you're going to, trust me, need it. So hopefully you've got those formulas written down, and we'll advance on to see what's next. So we're going to see, obviously, the circuit characteristics change just a little bit. Values in parallel RL circuits are calculated in a similar manner to the method used for parallel resistance. You got to consider the phase relationships, though, of the resistors and the inductors. And we're going to see exactly what happens in this lesson. So let's begin. Total inductance of a parallel circuit is always less than the smallest inductor. So we've got L1 of 6 millihenries and L2 of 3 millihenries. And guess what? We apply the same formula we did for resistors in parallel. And that's going to be the product over the sum or the reciprocal. We can do either one. And as we get there, we'll see that. And I'm letting you read each of those things up top. Obviously, it's telling you some things, and you'll be going through this lesson hopefully independently, but I want to go through some of the calculations for sure with you. So again, it's showing the product over sum formula. We'll do that. So that's basically 6 times 3 over 6 plus 3. So I'm going to say 6 times 3 equals, and I'm going to divide that over 6 plus 3, which is 9. And we get 2. And again, that is the product over sum. We multiplied 6 times 3, got an answer of 18. We added 6 plus 3, got an answer of 9. Did the math, and got 2. But we can also do the reciprocal if your calculator has a reciprocal button. I'm looking. I don't honestly see that this calculator does. And normally the Windows version of the calculators, go back to the standard. Yep, it does. This is your reciprocal button right here, the 1 over x. So if I say 6 reciprocal plus 3 reciprocal equals, and get the reciprocal of that, I get the same answer. So either way I get 2, whether I do product over sum, whether I do reciprocal, that's up to you. The reciprocal is easier to me when you have more than 2 in parallel. So again, it shows you that product over sum, shows you the same math that we just reviewed a moment ago. So I'm not going to go back over that, but if you want to look at that, pause the video. All right, so we've got a 5 and a 10. I'm going to do the reciprocal. I like it. We'll do both though, just because on this one, because I want you to see that both of them work. So I'm going to say 5 reciprocal plus 10 reciprocal equals reciprocal. And I come up with something that doesn't make a lot of sense. I must have hit a wrong button. So I'm going to say 5 reciprocal plus 10 reciprocal equals, and I'm going to reciprocate that, and that looks a little better. I came up with 3.3333. So forth. So that looks more like what we would want. But if we do the product over the sum, and I don't mind doing that one with you, it's just a little more involved in my humble opinion. We're going to have to say product 5 times 3 over 5 plus 3. So if we do 5 times 3, I can do that math in my head. Again, if you need a calculator, feel free. That's 15 over 8. Now, I can't do that math in my head. Oh, wow. Where did I get? I got the number off the calculator. My bad there. And sorry for the confusion. I know you're probably wondering what's going on. I'm not going to start the video over. But I am going to use the right value, so let's try that again. So let's say product over sum. This time with the right values, 5 times 10 over 5 plus 10. 5 times 10 is 50. 5 plus 10 is 15. And again, can't do that math in my head, but we're going to divide 50 divided by 15, and that's going to give us, no surprise, 3.3 henries. Now take note, both these units were in base units of henries. If we'd had a henry and a millihenry, we would have had to convert it to similar units. That was not the case here. So we did the simple math. We got 3.3333, so forth, and still on the calculator. So we'll choose our answer. And here it is. So easy one there. This is where you're going to definitely like, and this is the last one I'm going to do product over sum. You're welcome to always do product over sum. I prefer the reciprocal formula, and this one is going to be why I do. So I'm going to do my reciprocal formula first. 3 reciprocal plus 3 reciprocal plus 3 reciprocal equals 1. So the answer I got using the reciprocal formula was indeed 1 millihenry. If I can get this thing all right, 1 mH. So that was using the reciprocal formula. Now to do product over sum with more than 2, we have to do 2 at a time. We can't do all 3 at one time. So I have to literally do 3 times 3 over 3 plus 3. And we're saying we're doing L1 and L2, and we're going to get an equivalent value of L1 and L2. That's 9 divided by 6, which equals 1.5 millihenries. So now I have to do that value for L1 and L2. I have to say 1.5 times 3 over 1.5 plus 3. So 3 times 1.5 is 4.5, and 1.5 added to 3 is 4.5. Any number over itself equals 1. And we came up with the same answer using product of sum. So again, we had to take the first 2, get an equivalent value. So this value right here was the equivalent value of L1, L2. Then we had to take that equivalent value and apply it with L3. So 1.5 times 3 over 1.5 plus 3. And we had to do all that extra math just to get what we did with the reciprocal method by reciprocating all 3, getting the answer and reciprocating that. So again, your choice, but from this moment forward, I will use simply the reciprocating method. So let's clear that out. We got an obvious answer of 1 millihenry. We're going to see if that's right. And it is, so good. All right. So let's discuss inductive reactance in parallel. Inductive reactance is the opposition to current flow. And we already know that. XL, measured in ohms, is dependent on the value of inductance and the frequency of the circuit. So we have to take that in mind. So we already know the formula for inductive reactance. If we hadn't got that down pat, we're already in trouble. X of L is equal to 2 pi FL. Should know that from previous ones. And again, we can take the individual values. We're getting X of L1. We're saying 2 times pi, which is 6.28. We're taking this 1 kilohertz that's down here, and we're taking the 30 millihenries, which is the equivalent of L1, and we're coming up with an X of L for L1 of 188.4 ohms. Doing the same thing here, except the only difference is we're changing to L2's value 6.28 is 2 times pi times 1 kilohertz times 60 millihenries, which was L2's value. Now, oops, I think I advanced a couple of slides here. So, in order to get x of Lt, we have to apply the product over sum or the reciprocal to that. So x of Lt, if we have individual x of L's, is product over sum. XL1 times XL2 over x of L1 plus XL2. So again, it's product over sum, but for more than 2, we could do reciprocal. And so they multiplied the equivalent values of 188.4 times 376.8 over 188.4 plus 376.8. So would that work with the reciprocal? And I moved your window, so let me fix that back. Let's see. So let's go to our trusty calculator. Let's clear it out. And let's say, it's 188.4 reciprocal plus 376.8 reciprocal equals, and if we reciprocate that, we come up with 125.6, which is the same answer that they got. So yes, it does. And we can use either one of those. It's totally up to you at that point as to whether you do. But again, I like that reciprocating formula. So let's move forth. All right, so we can also go ahead and find x of Lt. Now remember, we can't just add these or anything. We've got to do that reciprocal or that product over sum. Again, I'm not going to force you into whichever one, but that's your choice. And that equivalent for this circuit is 20 millihenries. 30 times 60 is 1800. 30 plus 60 is 90. Divide that into 1800 and we get 20 millihenries. And again, if these values were not in the same units, we would have to do the math first to do that. But thankfully they were. So now we can get x of Lt this way, simply by applying x of Lt to pi FL to the overall XL L value that we get for Lt. So again, it's our option to do that. And once we do that, we arrive at 125.6, which is the same value we got when we reciprocated or product over summed the two values for L1 and L2. So here we go. We get to apply it now. So again, we can do this one or two ways. I'm going to do this one both ways just to let you see it. First thing we've got to do is we've got to get the x of L of each one of those. So let's get the equivalent one for the 30. Let's get the equivalent one for the 60. And we know x of L, here, x L equals 2 pi f L. That should be drilled into our brains at this point. So coming over to our calculator, clear it. 2 times, I've got to go to scientific to get pi, so let's change. Let's clear and start over. 2 times pi times 5 kilohertz times 30 millihenries equals. So what I did was, and just to let you see that, 2 times pi times 30 millihenries times 5 kilohertz. And I swapped out my frequency and my inductance, but that's okay. It doesn't matter if we put them the other way. The important thing here is we've got milli, which means divided by 1,000, kilo, which means multiply by 1,000, and they're going to cancel. So we're back to base units there, so we don't have to do a lot of math there. So we came up with an equivalent value of 942 ohms for this guy. So let's go back and erase our math here.